Fourier talks, I have a couple of announcements. We again would like to advertise the Birkhäuser-Springer exhibition in the lounge room. Please go and check the books that they had. Those are great books. And Birkhäuser-Springer does support us, so we would love to support them as well. For those of you whom we promised travel support, we would really like to ask you that you remember to pick up the form from Dr. Shaw outside and fill it out and send it back to us with all the receipts. And also, I would like to mention that the Norbert Wiener Center will have an open postdoctoral position starting this fall. So if there is anyone who would be very interested in working with us, please let us know. And now it's my great pleasure to introduce Justinian Rosca. Has a title that fits this economic situation very well, doing more with less. Thanks
for the invitation to come here. My name is Justinian Rosca. I'm from Siemens Corporate Research in Princeton, New Jersey. So I'll be talking about some joint work with Heiko Clausen and Professor Paul Tamber from the University of Southampton. Now, there are two ideas in the title. I have to introduce you to something called interdependence analysis. I bet there are lots of experts here on PCA, principal component analysis, ICA, independent component analysis, minimum component analysis, XCA, LDA, CCA, canonical correlation analysis. Mamma mia. All right, so that's Mia. Yet another technique. And I hope to convey to you that I can do something using a simple linear technique that's in the class of linear techniques, rather than jump into more complex things. Really, the motivation, the way we started thinking about this simple idea, as we're realizing here, is real data, very noisy data that's coming from a physical process. Basically, all you see is noise. And, well, I like to understand something about the physical process behind it. I like to, the general problem is do classification in here. Given a sample, can I recognize it comes from this process, right? It could be a piece of machinery, it could be some measurement of biological data, etc. Note that maybe I have lots of samples of my signal, so that's B, the dimension, and maybe I can get a few observations, N. And my case is N is smaller than B. I'm in trouble somehow because statistical techniques apply exactly in the opposite case when I have lots of observations. So let's see what I can do in this case. However, the idea is that I would like to characterize my data set in a succinct manner, unique eventually if possible, and be insensitive to noise. If my data has small variations, I'd be able to describe it in a similar way or not. So that's what MIA is about. Now, let me relate, that's a pretty much abstract problem that actually comes from the industrial problems that we have at Siemens and medical problems as well. But I'll relate to two very discussed, very much discussed topics in the literature, and one is speaker verification. That's still an open problem in real environments, noisy environments. Can I verify that the person talking right now is Justinian? Just giving a sample of 1 second of speech. All right, so, well, assume that I have various samples of speech that represent different situations, possibly different channels, different, emotional states, and so on. Well, that's the spectral domain representation for various situations. And as you see, there are similarities, but there are also some differences, some big differences. Well, the question is there something that's representing the physics of the process, right? So there's a vocal tract, there's like a unique physiognomy for person X, person Y. I'd like to capture that somehow, you know, is that possible? Does there exist an invariant representation? Now, a second very popular example over the last 10 years, that's face recognition. Well, we still have the challenge of, you know, dealing with different illumination conditions, multiple illumination sources, and things like this. And people come with more and more complex methods involving 3D representations of the face and so on, you know, modeling of diffusion, reflection, and so on, you know, very, very complex methods. And in the end, apparently, the devil is in the details, you know, it's hard to explain differences in performance. I will take a look at some, you know, simple data that's available. Again, my goal is, you know, I have extremes such as illumination, multiple sources, left, right, and so on. Does there exist an invariant, you know, characterization of data? And I'm highlighting again that maybe I have 10 images. I don't have thousands, tens of thousands, hundreds of thousands of images of a person, you know, illuminated from various positions. Right? So, well, there's some commonality between these three problems that I'm mentioning. And one is, you know, consider our observations can be modeled in this way. There's some unknown, hidden, invariant information S plus some other variant pieces of information, you know, from observation to observations. I'll have these variable parts, Fi, right? And I'm making the assumptions that S is orthogonal to this additive component, Fi, and Fi is orthogonal to Fj for a different rubric for the time being. So, well, really, in a simple way, I don't know if this is possible, if it makes any sense or anything, that's how we started to look at very, very challenging data. You know, can I extract, if there is any such common component representing the physics behind the process that's letting me observe, measure the data? You know, can I come with an estimate of that S? All right, let's see. For speech waveforms, well, it's well known that, for instance, voice speech, here I have she, that's a voiced part and an unvoiced noise really part. You know, so we know that voiced, for instance, the voiced parts could be modeled in the log spectral domain by log of h, the vocal tract, the excitation, and the microphone channel, whatever, you know, the rest. And well, for long term, and I come to this other idea that I said, I assume I have a large number of individual measurements, samples in each observation. These, the dimensionality of my data could be large. 1,000, 10,000, 100,000. Okay, so for long-term characterization, you know, I can make an assumption that this is a constant, but those are not necessarily constant. Well, so that sort of fits a model, the simplistic model that I was talking about. All right, and well, could I capture, you know, some independent element there, and eventually that perhaps that would include this log of h. For images, faces, you know, we know the illumination model of Fourier and Van Dam. That's very well known. So each pixel illumination is given by the ambient part and the directional part. So that's additive superposition. If I have multiple light sources, I would continue to add. Of course, those are modulated by the direction of the light source and the normal to the surface in that particular pixel. All right, so again, can I capture some invariant component which would be present in like 10, 15, 20 images from under various conditions. That would be my mutual image. In the previous case, that would be my mutual speech signature, let's say. All right. I will talk about MIA, which is a really simple technique for doing just that. And we'll take a look at alternatives. Now, you all know all those other Mamma Mia techniques. I'll relate what we do with some of those. There are very many similarities, linear regression, ridge regression, and so on, so it's hard to explain the tiny differences, actually. We'll go into a generalization based on a Bayesian interpretation. And what we did, we constructed a synthetic model. If my assumptions are correct, I should be able to generate synthetically some data, have some underlying, hidden, right, unknown, common components that I would like to extract. And we'll take a look what we do in these two typical applications from the literature conclude. All right, so, well, I have data from a given class or representing, an entire database. So we often look at a scatter, right, along the direction W. So, the scatter is clear and very simply defined. Now, PCA would involve these scatters. So of course, I'm interested in directions that maximize, right, the variance of my data. So this principal component analysis, LDA would look at intra-class. We have the between class is scatter matrix and the within class scatter. And well, so that's R max of this ratio of determinants, which would be solved as you well know. That's a Rayleigh problem. It would be expressed as well like that, so I might just highlight the scatter computed for the whole data and for class E of data. What MIA does, it's a similar formulation, but you will see that there are some fine differences. Okay, so we look at the scatter in the direction W. However, we constrain to be in the span of the inputs of the original data. That sounds like a strange constraint. And then we will see exactly why we do that. But essentially, what MIA does is R mean of this. Well, you will say, like about 15 years ago, people who started Karbunen and that's Paul's are here actually, Finland, and others were looking at minimum principal components. Well, isn't that the same? That's the MCA minimum component analysis problem. Well, basically, when we have few inputs of high dimensionality, the MCA problem isn't really defined. It doesn't work. It doesn't say anything. Right? So, okay, I highlight again that we confine a solution to be in the span of the inputs. And that's what we originally did, and there are some reasons why we did that. And I'll not go into all the details, but I'll show you alternative interpretations of these criterions that will make much more clear what exactly is happening there. Right, well, if inputs are linearly independent, there exists a unique MIA solution. And this is a solution. It can be relatively easily demonstrated that. So that's a one constant vector. Right, you see the ground matrix of inner products there, X transpose X to the -1, of course. Independence means that this is invertible. I can compute that inverse of the Gram matrix. And all right, so that's a nice property. Okay, I have a unique solution up to a constant level. Well, now multiply by x transposed here, and you will see that, so W is really a column vector here, right? So multiply by x, and you will see that you get 1 basically. So what does this tell us? That the solution W of mi is equally correlated. So basically we found something that's very, very simple criteria. Equally correlated with all the inputs, and also it is in the span of inputs. Right? Well, now a gram matrix times that is just, you know, a constant vector. Let's assume data dependent. Right? So we have a transformation that really indicates that this is a linear combination of inputs, of all the inputs. By x, by the way, I just concatenated all the concatenated all the inputs. Each observation is a column vector, and I put all the faces together, all the sums together, right? Right, so Mina defines this mutual feature in the input space. So let's see a few other properties. Assume the regression problem, y equals x times beta. So what is beta such that the unknown regression is equally correlated with all the inputs? You guessed, the solution is given by Mia. So that's a relation with linear regression. Okay. Let's take a look at, so I still have like a question mark. Why in the space of the inputs and so on? And let's take a look at the alternative, the interpretation using canonical correlation. And okay, so let's assume there is a common source S that influences. So again, we are already in the context of what we want to do. We want to discover these common sources, right? So the canonical correlation is the right tool to take into account. Two data sets x in r to the d times n and z r to the k times n, different, possibly different dimensionality, right? So canonical correlation would look at this criterion that involves projections on a direction of data x and projection on another direction of data z, right? And normalization here. And basically we maximize, right, the projection simultaneously w. So we tune directions w and u so that we have a maximally correlated projections. And the intuition is that those correlations, right, those correlated projections would represent an estimate of the common source. All right, that's classical canonical correlation analysis. Now, let's consider that there are some fine details in what we've talked about so far that maybe I glossed over. So in PCA you have 0 mean inputs, and in ICA the same thing, and you know that's the whitening of the data, and that affects the way we can process our data. In general, by subtracting the mean of the data, we reduce the dimensionality of the data by 1. So, well, here with CCA it's the same thing. We will take the original inputs rather than the mean subtracted covariance matrices. And consider the classification table. So let's say we have data from multiple classes again, K1 to K. Okay, and what are the class membership? What's the class membership table? That is for input I, input xi. You know, xi can represent data from class K. Well, then zki would be 1 if and only if xi is in class K, right, and 0 otherwise. Well, but I'm really interested in a trivial case. As I said, I'm looking at the local properties of my data. That I'm only interested in one class, really. You know, so that my membership table is 1. It's a vector, a constant vector 1. okay? Because, right, so I only have one class. So in that case, what does this modified canonical correlation criterion do? Well, it turns out that it completely simplifies, you know, the second direction. That doesn't really matter. It's super. So the criterion converts into what is a direction W such that W transpose X times 1 normalizes is maximized. All right, so that can be solved easily. Derivative with respect to W is 0. It goes for like a few easy steps. And surprise, this criterion is exactly our mutual interdependence analysis criterion. So what do we try to do? We try to see, is there like a common source in the data that explains that all the data is in the same class? That's what we basically did. So, you know, we know solutions are equivalent up to a constant. Now, these interpretations allow us to come up with some deeper understanding of what's happening there. So, corollary 1, the problem has no defined solution if the input are 0 and 2. So, you know, we avoided that. We didn't subtract the mean. So, right, so this is 0, of course, the problem is undefined. Corollary 2, any combination W plus U with U in the null space of X of the original data that exists, remember the constraint on dimensionality, right? N is less than D. Okay, is also, so that's non-void, right? So that's also a solution, right? So we actually have an infinity of solutions. We like to fix on one, and we can do that by putting these additional constraints that we are in span of inputs. Furthermore, the solution, that's a very interesting property. Solution reduces to the mean of the inputs in the special case when the covariance matrix has equal eigenvalues. So this could be proven, that's a nice proof of that. Well, so in general, however, the NIA solution will be very different from the mean of the data set. So we have something like analogous to the mean of the data, but it's not the mean of the data. It has like different properties. It has some interesting properties. All right. Well, I need to understand one more thing. Well, what happens if I have slight variation in the inputs? What happens with this criterion? What will it compute? You know, is it really sensitive to small variations in the inputs or not? The other part that I'd be interested in is to see, well, how different from the mean. We said that in most cases, yeah, we take some data, we look at images, so on. We get actually on the very noisy data, we get interesting results. We get an understanding of the structure behind the data. And that's very different from the mean of the data, which would be noise, pure noise. Okay, so we'll take one more step, you know, in this adventure. So Bayesian, take the Bayesian, well-known Bayesian linear regression model. So, okay, we have y is x, a vector of random variables, times beta plus noise, right? These are my observations. So, assume noise is Gaussian and beta prior is Gaussian with mean, mu, covariance, okay, and these are independent. So, well, so I have some priors on beta. Now, what is the expectation of the random variable once I see more data, right? So that's a conditional expectation. That's the optimal solution as defined in many books. I give this reference here of K. Okay, so that looks something like this. Expectation of beta given y depends on all these things, including our assumed parameters here. So that's a minimum mean square error estimator. All right, well, let's twist our model a little bit and go in a direction that we would like to have equal correlation between these summarized features and all the observations. So take R x transpose times W plus N, so that's like already a fine change there, okay? Well, we could assume that's to be some measurement noise, right? And W, right, so it has some distribution, some priors. Okay, now, we have an intended meaning for R here, right? Our observed data, and that is a vector of observed projections of inputs X on W, right? While N is 1, right? So ideally R is 1, and these correlations, right? That would be consistent with the criterion that we have in mind for MIA. That is a variance of projection to 0, which is exactly MIA, right? Criterion. Well, what happens in this case? Well, we just apply this and we just replace mot à mot all the components. And we can go on and look what really happened there. So, okay, so one interesting thing that will allow us to look at the relationship. So we glossed over, we made some assumptions, but that will formally let us analyze the relationship between the mean of the data set and the W. We call this generalized MIA, this formula, right? G-MIA. And we call it G-MIA for one clear reason is that, you know, it becomes identical to the MIA computation once we take CW to BI, so that's different betas are statistically independent. And mu W to be 0 and noises to be non-formal independent. All right, so in general, right, we want the MIA representations to be robust to small variations in X. So we'd like to see what happens in case we have such small variations in X. And eventually we like to parameterize our solution. And I will show you exactly how in order to be able to analyze and see if this general model, minimum square error, you know, model, estimator, sheds light on what we do. Okay, so I like to define, to understand a little better, I like to define what some artificial data and play with it. So my observations are combinations of S plus functions F plus noise, and I'm taking the F to be combinations of basis functions from a given dictionary, like the Fourier dictionary, of a given size, all right? And we keep these assumptions that Fj is orthogonal to Fi, and S is a combination. S is fixed, is different, is a combination of basis functions that's not used in any of the others. All right. And all right, I have some coefficients here, A, B, C, to be able to control the energy in each of those components. My case of interest I started with was the energy in some presumed S, if there is anything that represents a physical process behind, is very small. While the others, you know, components are dominant. We'll be able to play with that and see if that really gives us anything interesting. Okay, so A, I are scalars, typically close to 1, and B, C scalars, well, possibly very different orders of magnitude. And I'm just giving here an example, you know, that for instance, D is dimensionality 10,000, N is 20, whatever. So I have combinations of 10 basis functions. S is known, of course, and coefficients, for instance, A's could be slightly varying from one observation to the other, this way, meaning one some standard deviation, and so on. These could vary widely, could be completely different measurements, whatever. C, some noise probably doesn't matter here, but in other cases it would matter. All right, so I'll do the following as well. So I'll consider lambda parameter lambda, which is a covariance of the noise matrix. Now, with the assumptions that I made about CW, mu, I'm trying to simplify things as much as possible to play with the formula. I'll get some things that looks like ridge regression, linear regression. It's not really ridge regression, but it's very similar. With that, I have this constraint here of equal correlatedness. Okay, and now here is an interesting part. If this lambda is 0, I will get Nia, as we noticed before. And if it goes to infinity, if it's a large value, this formula converts into the mean. All right, so now I have also a handle on how to play with this big data generation process and see what happens. And I'll give you an example, and then we'll go to the real examples. So, okay, that's our model, and here are some values. And we have 20 observations, and 3 of them only are plotted here. So that's look like noises. Yes. 5 minutes? 2? Okay. All right. Well, that's the unknown component, S. This is what G Nia gives us with lambda input there, lambda equals to 1. And that's a mean of the data. And then I played also with principal independent components. Now, out of all 20, I look at correlations between those components and my unknown hidden whatever source. And PC9 is similar, but much noisier. In this case, independent component 13 looks like that. Still doesn't manage. In other cases, one can do various experiments, and all these other techniques look very, very different from what you'd expect. Well, now we can play with this lambda parameter, and we can play with the other parameters to generate a number of cases. Like, for instance, inputs are approximately equal. Well, here for each value of lambda, I have a number of experiments, and I have a distribution of what does generalized Nia mean. And you see this virtually a variance 0. It has a very clear computation, which is actually the mean, for large lambda. But there's a wider distribution when I re-implement the Nia formula. When inputs are approximately equal, well, when we have a common component, S, right, and here I have B has this middle component has a lot more energy, I would be able to extract the common component. So that's on the y-axis. I have the correlation with S. Basically, that's 1. This means I am able to extract S. And in this case, when inputs equally contain a common component, which is the assumptions that I made initially, eventually that satisfies somehow in the data, in any data. That really manages to extract something that's very different from the mean. The mean, repeating experiments, mean would jump all over, would not give any consistent results. All right, well, we discussed this text-independent speaker verification. I will not go into details. I'll just tell you that basically the bottom line here is what is the equal error rate. And strangely enough, equal error rates are comparable to very complex techniques that are published in the literature. And I will not go over results here. Same thing for phases. We do the FFT into the two-dimensional FFT, we filter the data, we do neon columns, neon rows to match somehow, and then we combine and we get these mutual images, and then we evaluate it on this Yale database. That's we have various illumination conditions and so on. But this just shows you one particular how data is actually considered in various approaches. But I don't think I have time to go over that. I mean, I will just conclude that again, that's a relatively simple technique. It gives low error rates in face recognition. Okay, well, I think I'll just conclude saying that NIA defines a simple invariant representation for a data class, or neutral, what we call a neutral feature of the class. That there are some interesting properties. First and foremost, there exists a unique neutral feature, right? And it's a linear representation, but interestingly yields some competitive results on some challenging problems. It still remains, open to look into the statistical properties of what exactly happens there. Thank you.
Thank you very much. Is there a question to the speaker? Yes.
I don't do image processing, and I probably haven't annoyed enough people here yet at the meeting. I wonder whether the basis of facial recognition is actually correct in the first place. We're trying to train a computer to recognize the face the way we do, when in fact we're really lousy at it. Any police department can tell you from their false positives and lineups, we're lousy at facial recognition, and we want a computer to act like we do. My wife, on the other hand, is a mathematician and an artist. She can go to a party, come home, draw you 5 lines on a sheet of paper, and you'll know exactly who she meant. Is there work being done, in a sense, to imitate how an artist sees a face, right, instead of the way the rest of us do?
Recent work really looks into features and relation between features and so on, like going into higher level representations.
Well, no, I understand that we do feature analysis, but we do it from a non-artist point of view. That is, even the features we're looking for are not the ones she looks for.
Well, Peter, that's one of the grand challenges in artificial intelligence that's still open. You get an image of a horse, you immediately recognize a horse, right? But the computer can hardly recognize a horse.
Okay.
It's unclear exactly how we do that. I think there are hypotheses, obviously. Cognitive modeling and so on, how all these things works, and there are models of vision, right? But in the end, it's still really difficult to do it automatically.
Well, let's thank our speaker again.